Friends, a couple of years ago, nearly 300 billion chips or semiconductors were sold worldwide. It's about 40 chips to a person on the planet. Chips are classified on logic and memory. Logic chips perform operations or are really the brain. Memory chips store data. Its material has electrical conductivity greater than an insulator but lesser than a conductor. That's the reason it's called semiconductor. Simply put, a semiconductor as a material uses electricity in a regulated manner as required. That, friends, is the subject of discussion for today. That the government is planning to incentivize setting up over 20 semiconductor design, components, manufacturing and display fabrication units, over the next 6 years, worth almost 76,000 crores, could be a great move to make India a hub of electronics. That said, much more needs to be done. However, detailing for inviting applications for such manufacturing hubs would be the real key. In 2020, the semiconductor industry in the United States accounted for 47% of the global market. South Korean manufacturers are second in the world, with about 20%, with companies from Japan, the European Union, each accounting for a 10% of the market. In a sense, India will be making some baby steps important for the global market pie. Sankhya Labs, ASM Technologies, Broadcom.Inc, Chip Logic Technologies, CDIL, and some others currently rule our country's manufacturing space. A semiconductor company usually either manufactures silicon wafers or design chips produced by other companies. Such an Indian initiative should have come at least a decade earlier. And that's the truth. That it has happened now is an opportunity. Globally, there is a shortage of semiconductor chips that has affected the production targets of almost all the industries. And almost all the industries use semiconductors in one way or the other for their control systems and so on. Today, there is no equipment which does not use semiconductors. That's the fact. From automobiles to washing machines to entertainment equipment to digital devices, IoT, they all use semiconductors. The cost of a semiconductor chip fabrication in a company doubles every 4 years. Hence, only those manufacturers who can up the production without delays will obviously benefit. Semiconductor manufacture is extremely technology and capital intensive. It would be an uphill task without adequate enabling provisions that support the various supply chains that are around the semiconductor industry. Mere capital subsidies will not help, as was seen in the past. Let's understand the process to know the complexities involved. Firstly, semiconductor devices are built up in a series of nano fabrication processes performed on the surface of substances made from highly pure single crystal silicon called a wafer, which allows advanced miniaturization required for cutting-edge devices. The materials used are silicon, germanium, gallium arsenide, and silicon carbide. Now, whereas Hemlock Semiconductor Corporation and Okmetic are the largest manufacturers in the world, Sankhya Labs, ASM Technologies, Broadcom.inc are all based in India and much smaller than the world leaders. Now, these silicon wafers used as a base of the semiconductor are then cleaned to remove all contamination like ultrafine particles or the oxide layers that are formed because of the interaction with the atmosphere, and they all form defects in the circuit if they are not removed. This is followed by a very tricky process of sputtering and electrodeposition, where layers of silicon oxide, aluminum, and other metals are deposited to form micro-thin films. These are the circuit materials on the wafer. Another cleaning round follows, where superfine particles that may be still adhering to the wafer after the film deposition are removed using nano spray with deionized water. No reactions must take place at that point of time. The wafer surface is then coated with a photosensitive chemical called resist, after which the wafer is spun, causing a uniform layer of resist formed on its surface through purely centrifugal action. Now for the most important part of the step, where the wafer is exposed to short wavelength deep ultraviolet radiation projected through a mask on which the circuit pattern is formed. Obviously, only the layer of the resist layer that are exposed to the light undergo a structural change, thereby transferring the pattern to the wafer. When the developer is sprayed onto the water, it dissolves the areas exposed to light and reveals the thin film on the wafer surface. Remember, there are still those remaining resist areas which are not exposed. So they become the mask for the next etching process, where the exposed thin film on the surface layer is dissolved using chemicals such as hydrofluoric acid or phosphoric acid, forming the pattern. Next, for the semiconductor property to be realized, impurities such as phosphor or boron ions are implanted or doped. They are put on the wafers. In order to activate these doped ions, of maybe boron or phosphor, flash lamps or laser radiation is used, which is extremely critical for its need, and it must happen instantaneously. Now the resist has to be stripped off at a wet station that uses chemicals, and finally dicing follows, where the wafer is separated into individual chips, then connected to a metal frame or a lead frame using wire bonding, and then enclosed in epoxy resin material termed packaging. Now, what makes the process doubly challenging are the scales involved, size involved. Nano, most of the times 10 raised to minus 9. Now, the environment and fabs for manufacturing are enclosed areas with strict controls for airborne contamination, humidity, and temperature. Great quality control is the key. So as many as 500 different steps are needed to process the wafer. Since layers of material are deposited and removed for the desired patterns. Since the process is complicated, controlled, and needing very high technology levels, the return on investment is realized only when the numbers are exponential, and the return on investment also happens through exports. In as much as saying that our country must be there where technology matters, but that is the only way to compete in the global market, there is a flip side. A typical semiconductor fab every month makes about 2 million integrated circuits per month, every month. In doing so, it uses about 20 million gallons of water, which is then disposed of as waste. Should this be a concern? Our universities should do well to look at the alternatives. A high amount of energy too is required, apart from using many toxic chemicals which can harm the environment. They all flow through the water, maybe let into the rivers, the seas, and so on. Comfort comes at a price. Economic strength comes at a price. One-upmanship comes at a price. We need to tread judiciously the chosen path. The nation must set up an ecosystem for semiconductor markets to thrive, but not at the expense of health and the environment. Not everything may be possible to manufacture here. The high environment risk processes must be outsourced. Collaborating with foundries may be local or global, and assembly houses must be encouraged. Partnering with integrated device managers, IDMs, will be a great idea. Friends, semiconductor suppliers must be incentivized. Engaging with customers before manufacturing unit is started, and engaging in design must all be practiced if the semiconductor industry is to survive. Our manufacturers must think vertical and not develop IP blocks, but buy them if they are available. I leave you to reflect upon tomorrow, the Sunday, and with a promise to be back the next Saturday. Until then, I remain. Thank you, Dhanyavad, and Namaskar.